Hello, my name is Jeffian Lin. I'm from National Sun Yat-sen University. First of all, I would like to thank the organizers for inviting me to this special session and also handling this video form of presentation. The video and the slide will be available online. You can simply search for Jeffian Lin and it will be available on my personal website. So today I'm going to talk about the inverse eigenvalue problem. The inverse eigenvalue problem of a graph in particular is abbreviated as IEP-G. It will talk about a graph. A graph has a structure which has some vertices and some edges. Okay, and we are going to use the edges to describe the non-zeroness on a matrix. So the vertices will be the indices of the row and the column. We are going to consider the real symmetric matrices such that the off-diagonal entries whose zero and non-zero are described by the edges. So for example, here the edges are 1, 2, and 2, 3, and 3, 4. So we set these three entries to be non-zero. They don't have to be the same, but the whole matrix has to be symmetric. And the diagonal entries can be anything. So given a graph G, S of G represents the set of families that the set of matrices containing all the matrices of this pattern. So it has a lot of matrix. Once we pick one matrix from it, we can calculate the spectrum of that. But the inverse eigenvalue problem is saying if I give you some numbers, some real numbers, can you go back and find a matrix such that this matrix has the prescribed spectrum? In other way, the IEP-G is asking what are all the possible spectrum in S of G. So there are several motivation of that from the engineering perspective. You can think of this as a mass spring system, such that each node is a mass and the spring is the edge connecting them. Somehow you don't know the weight of the mass and you don't know the coefficient of the spring. So that's how you come up with this matrix. And the vibration behavior is governed by the spectrum. So we want to understand the vibration behavior provided that we are not quite sure about the exact value of the matrix. On the other side, it is just a fundamental question that we want to study a matrix like this. Whenever the only information is the pattern, what can we talk about the matrix? So that's the inverse eigenvalue problem. It can be a bit hard because the real numbers has a lot of combinations. So we will use the ordered multiplicity list in some case to simplify the question. It is just a notation. For a real symmetric matrix, the eigenvalues are always real and it can be ranged from small to large. So suppose lambda 1 to lambda q are the eigenvalues from small to large, and we can record its multiplicities, m1, m2 up to mq. We call this sequence as the ordered multiplicity list. Now think about the following question. Suppose the four numbers that I give you is 1, 2, 3, and 4, and I want you to give me a matrix whose support looks like this, and such that the spectrum is exactly equal to 1, 2, 3, 4. And so you can give a try by algebraic conditions, but another way to do so is by perturbation. We may start with a diagonal matrix whose spectrum is 1, 2, 3, 4, and do some perturbation that preserve the spectrum such that it creates some more non-zero entries. So here it just means it is somehow very close to 1, very close to 2, and the epsilon are non-zero numbers. And if we can do this, then basically we answer this particular question. Okay, this is actually called the Supergraph Lemma. It is doable, but there is one condition called SSP, which will be defined later. So here is a statement. Let G and H prime be two graphs on the same set of vertices, and H prime has more edges than G. So you can just think of that G and H are different support of the non-zero entries. The support of G has fewer non-zero entries, and the support of H has more non-zero entries. Okay, the statement says if A has a support on edges of G, and it has this nice property SSP, then there is another matrix A prime whose support is H prime, and the spectrum is the same. And also A prime is nice, has the SSP also, and A and A prime can be chosen arbitrarily small. So at the beginning of the talk, I want to give a sketch of the proof for this lemma, and because I think it is cool, it will utilize two concepts. The first one is the derivative of vector spaces, and the second one is the inverse function theory. So let's look at the matrix derivative. It actually works for any vector space. It's just the normal definition of the derivative, but I want to provide the point of view for the purpose of this talk. That U and W be two open sets, and there are open sets in the vector space, so you can do some addition and do some subtraction. F is a function sending U to W. The derivative of U at a particular point, U0, we focus on one point and we want to calculate the derivative. And the formula looks like this. We need the direction D, and it says that we're taking the U0, starting from U0 and going to a little bit of D and subtract f of U0. And this is basically the formula for the directional derivative. So actually, this derivative f prime or f dot can be viewed as the linear operator that sends a direction to the directional derivative. And the direction is in the tangent space of u. The directional derivative is in the tangent space of w. Okay, so here is an example. Fk is equal to e to the k, the matrix exponent. Okay, let's consider K is a skew-symmetric matrix, and we consider this function. And notice that when K is equal to 0, the function value is equal to e to the 0, which is the identity. And I'm going to calculate the derivative at 0. So at k equal to 0, we set u0 equal to 0, right? And where we want to go to a certain direction. We still call that k. We want to go to this direction, k and a little bit, and then divided by t. Using the tether expansion, you will see a lot of series, a lot of terms here, and somehow the last one is minus I because of e to the o. Now, taking 1 over t, you will cancel one of the t for each term, and this I will cancel with the first term. Okay, and after that, this one is cancelled with I, and the t will be cancelled. So this is only constant term, and the other things has a t inside. Therefore, when you have t goes to 0, everything disappeared, and only k is remaining here. So e to the k, the derivative at 0 is equal to k. And particularly, I want to emphasize that this function is important because when k is skew-symmetric, the output is always an orthogonal matrix, and which we will be using for the perturbation. On the other side, we need another tool, which is the inverse function theory. Roughly speaking, it is the following. Let's say f is a function, it is a smooth function. If f dot, which is a linear operator, if f dot is invertible at the particular points, then f is locally invertible around this point. That's the classical definition or classical statement of the inverse function theory. And somehow, we really don't care whether it is one-to-one or not. For our purpose, we just want to make sure that there is a point mapping to a point to the other space. So it can be modified slightly. I think it is this is also known, but the function is saying if we have a function again, but this time f dot is surjective. It is not necessarily invertible, but it is surjective. Then f is locally surjective around this point. So that means every point in the codomain, you can find the matrix or find a point in the domain sending to the codomain. It is locally surjective. So with these two tools, the matrix derivative and also the inverse function theorem, we're able to give the sketch of the proof. Let's recall the statement first. We have a matrix with a smaller support, and we want to perturb that without changing the spectrum, but now it has a bigger support. Okay, here is how we are going to do that. That this S be the set of symmetric matrices that is non-zero only on the blue entries. In this particular case, it is just the diagonal matrices. Okay, so S is the vector space. And we can define the following perturbation. We want the matrix B in this S, and we also want the skew symmetric matrix K. And the perturbation is the following function. We will do the perturbation such that it preserves the spectrum. Right? This is the orthogonal matrix. This is the inverse of the orthogonal matrix. And so after we're doing this, it preserves the spectrum. And B is try to perturb the matrix a little bit, but preserve the pattern. Okay, because the pattern of B just like this. Okay, and the mysterious SSP just says that F prime or F dot is surjective. We're not going to prove this, but just take it as a definition if you wish. The SSP, which we haven't defined, is basically guaranteed that this particular function is surjective when k is equal to 0 and b is equal to 0. So by the inverse function theorem, we can find the matrix M, which is very close to A. For example, we have matrix A like this. We can take the matrix M, which is like the orange of this matrix. So it is 1, 2, 3, 4, but with some epsilon on some target entries. Okay, so for every nearby matrix M, there is B prime and K prime because it is locally surjective. So we can find these two matrices such that the function will send B prime and K prime to this matrix M. And so that is great because M has a target, has a nice pattern, and B prime also has a nice pattern. B prime is a matrix which is a small value that changes the diagonal entries a little bit. So we just move B prime to the right hand side so that A prime is equal to M minus B prime. When B prime is very small, then the pattern is basically look like what we wanted. And more than that, A prime is similar to A. So A prime and A has the same spectrum. And this completes the proof. This proof is one of the main concepts that I want to deliver in this talk. And so for the rest of the time, I want to say more about the SSP. It is a bit technical, and I'm going to say what we can do using this SSP beyond this proof. So let's do some technical details. What is the derivative of the perturbation function here? So you can use the product rule to do the derivative of this one. It will give you minus k, which is k transpose. And recall that when k equal to 0, it is identity. So here is an identity. So the product rule will give you the derivative of this matrix here. And the derivative of b is still b itself. So at 0, 0, this is the derivative of the perturbation function. And where K is a skew symmetric matrix and B is the matrix in the set S we defined in the previous slide. And in general, the set S can be written as the topological closure of S of G, because S of G is saying that the non-zero entries happens on the edges. And the topological closure says that these non-zero entries can actually be zero or non-zero. Okay, so this becomes a vector space. It will be a bit easier to toggle with. So to talk about the surjectiveness of this function, it is not hard to see that f prime, okay, so, sorry, this is a mistake. F dot is surjective at 0, 0, if and only if the range of the function on the left-hand side and the S of closure of S of G, their sum is actually equal to the whole space of symmetric matrices. And so if you want, you can just take this one as the definition of the SSP. But somehow classically, the definition of the SSP is the following. The whole name is the strong spectral property, and it will use A, matrix A, to define a few equations. And if x equal to 0 is the only real symmetric matrix that satisfies the following three equations, then we say A has the strong spectral property. But somehow in this talk, we are not going to use this definition, but most of the time in the literature, you will find the SSP in this form. And equivalently, you can say SSP if and only if the following holds. So it's not so obvious, but these conditions and the sum of two vector space equal to the whole space, these two conditions are equivalent. So in this talk, you can just take the definition of SSP as the following. Okay, in the next slide, I want to generalize the SSP a little bit. So you can see that basically this K is telling you that I want to perturb the matrix without changing the spectrum. And this vector space is try to perturb the pattern a little bit without changing the non-zero entries, right? But somehow, if we are willing to perturb more entries, then we can do a little bit more. Okay, so in the next slide, again, feel free to ignore this part. This is the kind of the definition in the paper that used in the paper. But in this talk, we are going to define a matrix A has the SSP with respect to another graph H. If and only if everything is the same except for this space is a bit bigger. Think of G as the support of A. It is the smaller support, and H is the larger support. And previously, SSP is saying we are only allowed to perturb those entries in the support of A. But now, suppose we are willing to perturb more and more entries in a greater support. Then this is called the SSP with respect to a greater support. With this extended SSP, we are able to prove an extended version of the Supergraph Lemma. But first of all, let's look at this matrix. Here is what I meant by the extended SSP. If you just focus on the support of A, then basically it does not have the SSP. You can do some calculation. But suppose we are willing to perturb more and more entries, like including the entries in teal colors. Then this matrix has the SSP with this greater support. And once we have the SSP with a greater support, then we can do the similar kind of perturbation and make everything outside a little bit different, and also change the perturbing area, the support a little bit, so that the spectrum is different. So here is the statement. It is the extended supergraph lemma. Now we have three sets, three support, G, H, and H prime. And think of G as the support of matrix A, and the edge is the entries that we are willing to change a little bit. And H prime is the controlling area. We are going to change these entries to be epsilon. Okay, so suppose A is a matrix whose support is G, and somehow it might not have the SSP, but it has the SSP with respect to H. Okay, this is the loser condition. Okay, uh, then there is a matrix A prime that is in the topological closure of S of G, H prime, such that the spectrum is the same. A prime has the SSP, and the A and A prime can be chosen arbitrarily small. So pretty much the picture below describe this behavior. You can perturb the outside area a little bit, and so that the inside area will automatically change a little bit according to the inverse function theorem. So the key point here is if you are willing to perturb a bit more entries, then you can use the weaker condition to make everything work. You can still perturb the matrix. But the only drawback is after you perturb the zero a little bit, you are not quite sure whether it is still zero or it is non-zero. That's something that we need to take care of or be careful. Finally, I would like to briefly talk about some application of the supergraph and extended supergraph lemma. This is a known result. Suppose that H is a graph, and we can append a leaf onto H and call this graph as H prime. This known result says that if we have a matrix A in S of H with the SSP, then we can find another matrix A prime inside S of H prime, also with the SSP, and its spectrum is the same as the spectrum, but with one extra eigenvalue. And the only condition is that this extra eigenvalue is not part of the spectrum of A. Now, with the extended version of the supergraph lemma, we are able to do a little bit more. By that I mean we have a graph H and we want to append a clique, which means that we have S vertices and they are connected to each other, and also each of the vertices are connected to this particular vertex V. This graph is called H, and similar stories, we have A in H with SSP, then we can find a matrix A prime in H prime with the SSP, and this time the spectrum of A prime is equal to the spectrum of A along with lambda with high multiplicities. And the condition for lambda is the following. It cannot be part of the spectrum in A. It cannot be part of the spectrum of A taking out the rows and column of V. So with this appending clique lemma, we are able to find the following example as ordered multiplicity for this example. Thinking of H as this one, it has ordered multiplicity list 2, 2. And when you append a clique s equal to 2, then you can append another 2 here. You can append another 2, append another 2. So starting with 2, 2, you can append 3 copies of 2 in the ordered multiplicity list. And the whole idea is to start with a matrix of H and then add a lot of lambdas at the bottom, lambda I, and then apply the supergraph lemma. And all you need to do is try to take care of these zero entries. Make sure after the perturbation they are non-zero. But it is just too technical, and I think I will stop here. So thank you very much for your listening, and I'm happy to take any questions through emails.